If the greatest common divisor of a and b is d, then Bezoos claims that there are integer solutions x and y to the linear equation. We can find these solutions using the extended Euclidean algorithm. But remember, a good way to understand mathematics is to solve it again. Let's find another way using modular arithmetic. So suppose ax plus by is d. To introduce modular arithmetic, we need to choose a modulus. If we choose mod b, we can eliminate the y terms. So a solution to ax plus by equals d would also be a solution to ax congruent to d mod b. By the same argument, it would also be a solution to by congruent to d mod a. So, for example, let's try to solve 7x plus 11y equal to 1. This equation corresponds to the congruences. Solving them gives us since x is congruent to 8 mod 11, then x is 8 plus any multiple of 11. And since y is congruent to 2 mod 7, then y is equal to 2 plus any multiple of 7. And so our solutions are, or are they? While it's true that any solution to our linear equation will be a solution to the congruences, it's not true that any solution to the congruences will solve the original equation. So how do we find a solution? We'll need to do some algebra. So remember, you can assume anything you want as long as it's explicit. A solution to this equation will have the form for some values of s and t. So we can substitute those values into our equation, and we find. So we can solve for one of the variables in terms of the other. Let's solve this for t. And so this value for t will allow us to rewrite our equation for y. So if x equal to 8 plus 11s is a solution, then y must be negative 5 minus 7s. And as with everything, trust but verify. This gives us solutions if we choose a value for s. So if s equals 0, we get, and we can verify that 7 times 8 plus 11 times negative 5 is in fact 1. If s is negative 1, we get, and again we can verify. This approach worked in this case, but will it always work? Suppose we want to solve our linear equation. If the greatest common divisor of a and b is not a divisor of d, then this is actually unsolvable. But if the greatest common divisor is a divisor of d, we could remove it to get an equation of the form, and Bezoos' lemma guarantees a solution exists. So suppose we want to solve linear combination equal to the greatest common divisor. As before, we can reduce these mod both coefficients. We know we can solve these congruences, and so our solutions will be something of the form something plus a multiple of b and something plus a multiple of a. If we substitute these into our equation, we get, and now let's try to get rid of this at term in our expression for y. So we'll solve this for at. And so our solutions will be of the form. Notice that x will be an integer as long as s is an integer. But y has this fractional component, and so y will be an integer as long as this expression is an integer. And this would occur if this expression is a multiple of b. So note that this expression is going to be congruent to d minus ax naught mod b. But remember, ax naught is supposed to be congruent to d mod b. It was a solution to our congruence. And so we know that 0 is congruent to the difference. So we know that b does in fact divide this expression. Consequently, and so this expression is an integer as well. So let's find integer solutions to this linear equation. Since the greatest common divisor of the coefficients is 3, and 3 does in fact divide the constant, this equation does have integer solutions, and we might as well just remove that common factor to begin with. And now our coefficients are relatively prime. So now we can solve 4x congruent to 16 mod 5, and 5y congruent to 16 mod 4. And these have solutions. And if we substitute these into our equations, we find... And we can solve this for t to get... And we can now generate a few solutions.